Hey guys, everybody's doing okay? What we're going to do today is continue with our unit on kinetics, and we're going to talk about something called collision theory. Now, collision theory, I think, is pretty easy, and it really is just going to focus on what causes reactions to occur, and how can we get them to occur at a faster rate. So in order for a reaction to occur, a couple things need to happen. So number one is that in order for particles to react, bonds need to be formed or broken. I mean, that's the definition of what a chemical reaction is, right? Bonds are broken from their reactants, and then new bonds are formed. New substances are created. So in order to break and form bonds, particles must collide with another particle or a wall. Okay, so there has to be some collision, or really many collisions, that occur here in order for bonds to break and new bonds to form. Not all collisions result in the formation of a product, and actually very few collisions result in the formation of a product, which we'll see a little bit later. So our collisions, I should say, fall into two different categories. We have ineffective collisions, which are, that's when particles just bounce off of each other and really no change occurs. So most collisions are actually ineffective. But 1 in every 10 to the 13th collisions between hydrogen and iodine, just for one example here, is something we call an effective collision. So it depends on what you have. So sometimes collisions are more effective than others, depending on what reaction you're looking at. But if you're looking at H2 plus I2 to produce hydrogen iodide, you're looking at 1 in every 10 to the 13th collisions to be effective. And if that reaction occurs, and you know there has to be many collisions occurring, if only 1 in every 10 to the 13th is effective to make that reaction happen. Okay, so we're going to look at how could we get effective collisions, or how could we increase our opportunity or chances of an effective collision versus an ineffective collision today. So why would some collisions be effective and while others are ineffective? Let's see, we have SpongeBob and Patrick here going after a jellyfish, and clearly this is not going to end well for either one of these. And you can see that they do collide here, and they do just bounce off one another. Okay, so this is definitely an ineffective collision here. So why would some collisions be effective and others be ineffective, like the one that you just have on your screen here? A couple things we're going to look at. A bunch of these are actually a review from Chem 1 or Honors Chem. So we could talk about those as well as we progress through this list. So number one, particles need sufficient energy to break or form bonds. So the energy level needs to be there. So energy, the kinetic energy is really just temperature. So we have to be at a correct temperature here, or a certain temperature, for collisions to be more effective than ineffective. All right, so here's an example for you. We have A and B on this picture here. A is at the top and B is at the bottom. We just have two molecules colliding, so our blue molecule and our red molecule. Maybe that's the H2 plus the I2 that a slide or two is referencing, right? And for letter A, you can look at that. These two molecules collide, okay, right here. So they come towards each other, they collide, and it looks like they just bounce off of one another. So for letter A, it says slow moving, not enough energy to break bonds. So we need these two molecules to collide. They need to have enough energy for the bonds to break, okay? And then they need the new bonds to form, which clearly is not happening here. Look at letter B though, the picture underneath. Looks like we're moving at a faster rate. Okay, so we're at a more sufficient kinetic energy or temperature here. These two molecules are colliding, and it's right here. And you can see that the bonds are clearly broken and then reformed, and we have, it looks like, HI, two molecules of HI being formed here. So the H2 plus I2 yields 2HI. Looks like that's the reaction that's occurring here. So one underneath, the faster moving particles help our old bonds break and our new bonds form. So better your temperature, more kinetic energy you have, better your opportunity or the chance of bonds being broken and new bonds being formed. The Maxwell-Boltzmann distribution shows this really well. So I'm dwelling a lot on the first point here because it's really important. Some of the other ones we go through a little bit faster. But we saw Maxwell-Boltzmann distributions before, okay? So quick recap. X-axis, energy, okay? Y-axis, number of particles. That's important. So our energy goes from 0 to X. I don't know what our max energy is here, but you can see that we have two different substances here. We have our substance in purple representing the higher temperature, and substance in orange representing the lower temperature here, okay? So again, temperature is the average kinetic energy. That's really important. So here's your energy on the x-axis, and we have 0 to x, and we can see that this molecule here, or the molecules in purple, have a very wide range of energies, okay? But they average out to a particular amount, right? That's why temperature is the average kinetic energy. Same with orange. You can see that more of the particles for the orange substance are at a lower energy, so it's at the lower temperature, okay? So the purple is the high temperature, orange is the low temp, okay? And look at what you have here. The activation energy is in this blue, on this blue line. We'll talk more about activation energy at the end of the lesson, but it's the energy needed for a reaction to kind of get started, or to get over this little, like a hump almost. So you can see that this is at some level of energy here. Okay, I don't know what it is. We're just going to make up another variable here. Some amount of energy y, okay, is what we need here for the reaction to go. That's what the activation energy is. You can see that at a higher temperature, this purple line, more particles have this required energy. Okay, so here we are. Okay, number of particles for the purple line is higher. Look at the number of particles that have the required energy for the reaction to get going, which is this blue line. Look at where the orange line intersects that. Okay, so I'm just going to make up a variable. Here is A, number of particles, and here's B, number of particles, right, for the purple line. So more particles at the higher temperature have the required activation energy for the reaction to begin, okay, or to proceed. For the orange one, at the lower temperatures here, less particles, okay, have the required energy for the reaction to go. So the reaction is going to proceed at both temperatures here, at the low temperature and the high temperature. But at the high temperature, the reaction is going to proceed faster because more particles have the required energy needed for the reaction to proceed. Okay, that's the Maxwell-Boltzmann distribution. You're expected to know how that works and be able to explain that. And we're going to do a lab where there's a question about this as well. Okay, number 2, particles have to have the proper orientation. This is very easy to understand, I think. Here's our reaction. We have NaCl plus Cl yields NO plus Cl2. So in this case, we have NaCl needing to collide with a Cl atom. You can see the top row here. We have our Cl atom right here and our NaCl right there. They are colliding. And we want to create Cl2. Okay, that's telling me that both of these chlorines need to collide with one another. That's what's occurring here. So these chlorines are colliding. They collide effectively so they can bond together. And then our NO stays behind. Okay, so here's an effective collision for the top row. So we end up with NO plus Cl2. Look at the bottom one. Look at the bottom example here. We have the Cl colliding with the oxygen in NaCl. There's no way for the Cl to bond with the Cl on this side, okay? So we want to have the Cl and the Cl smash into each other, collide, okay? Here, you're going to have an ineffective collision because the Cl's colliding with the oxygen. So they're just going to bounce off one another. It's not going to happen, okay? A little clip here that we'll watch for another effective versus ineffective collision. You can see how the orientation makes a big deal. All right, so let's watch that and we'll move on.
For some complex reactions, such as that between potassium atoms and methyl iodide, the relative orientations of the reactions becomes important. Only when the potassium atom collides directly with the iodine atom will the reaction take place.
All right, number 3, concentration. So higher the concentration, the more collisions, and therefore a faster rate of reaction. So one way to get your reaction to proceed at a faster rate is to just have more and more collisions occur. So here is your low concentration, and here is your high concentration. All right, so remember, molarity, which is concentration, is moles per liter. So the higher your concentration, the more moles you have, the more particles you have. More particles you have, more collisions occur, and then the more collisions that occur, the faster your reaction rate is going to be. Okay, so that's number 3, pretty simple. Number 4 is also pretty easy. It goes back to a couple lessons from some previous units here on bond strength. So the stronger the bond, the more energy is required to break it, and therefore the slower the reaction is going to be. So you can see over here we have a lot of double and triple bonds. We have a high bond energy there. So I mean, look at the carbon-oxygen triple bond here. That would be in something like carbon monoxide, right? And it's 1,072 kilojoules per mole to break that bond. Or look at the carbon-oxygen single bond. It's only 358. Okay, so more energy is required over here. So therefore, if you have a typical, like a substance with lots of double or triple bonds, where they have these high bond energies and these very strong bonds, those reactions tend to happen a little bit slower because there's more energy required to break those bonds and to have the reaction move forward. Second to last one here, number 5, the state of matter. So gases have more kinetic energy. Right? Solids have very little, liquids have a little bit more, but not much more. Gases have the most and way more kinetic energy, so they move around faster, collide more, even though they're always more spread out than solids or liquids. So it's tough here with gases. They're spread apart, and they're very far apart, so they have a harder time colliding, but when they do collide, they collide at a, with more kinetic energy because they're moving a lot faster. Solids and liquids, they lack some of that kinetic energy. So while it's maybe easier for them to collide, the energy that they have is less for a slower rate of reaction. So a lot of different variables going on here for number 5 in this list. Last one is number 6, though. This is really fun to demo, and if we're in class, I could do this, but it's surface area. Hopefully I got to this demo in Honors Chem or Chem 1. The larger the surface area, the more collisions, and therefore the faster the reaction. So here is let's say a clump of magnesium, okay? And this is magnesium powder, so it's still magnesium, okay? But it's in a much smaller, size, right? If you add up all of the atoms of magnesium in this picture on the left, okay, that is going to be the same as the number of atoms of magnesium on the right, okay? Let's say we have a mole of magnesium, which is around 24 grams. You're going to have 24 grams of magnesium on the left, 24 grams on the right, but just in a smaller size, okay? So more surface area is the same volume, okay, same amount, but smaller particle size. If I drop that magnesium into a container of hydrochloric acid, for example, very fast reaction is going to occur here. If you take a look at it, all of the hydrochloric acid on the outside has to react with the outside, okay, of the magnesium first. Once the outside of it reacts, then the next layer could react, and then the next layer. The magnesium on the inside of this clump here isn't reacting for quite a while, actually. But if you grind that up into a magnesium powder or some magnesium filings and dump those into hydrochloric acid, then the hydrochloric acid will still attack the outside of these small pieces first, but there's not much to them, so it reacts almost instantaneously. So this is a very fast rate of reaction, and this is a very slow rate of reaction over here. Okay? This has to do with medication. So if you take a medication that is like a larger pill, like you could do that maybe once a week because it takes a long time for your body to absorb all that. Or you can take maybe a smaller pill, okay, in a smaller dosage, like every day or something like that, because it reacts faster. Okay, so that's a good real-life example there. And we also did a demo with lycopodium powder in Honors Chem, and we also probably talked about the Imperial Sugar Plant explosion in Georgia. Around the early-ish 2000s, I think, where sugar dust actually caused an explosion and killed a bunch of people and injured a lot of people. So that's another real-life example here. Okay, so I want to focus on temperature here a little bit and something I call the double whammy effect of temperature on the rate of reaction. So as you can see on the screen there, as the temperature is increased, the rate of reaction increases exponentially. So it's not a linear curve like many people expect. Okay, it doesn't just keep going up gradually and very evenly. It's actually a very exponential curve. You can see as the temperature increases, our rate really increases very quickly. So let's see why that is. Since the rate law, which we may or may not have defined yet, if we haven't, you still understand this, that's okay. Since the rate law has no temperature term in it, which you'll see if you haven't, the rate constant depends on the temperature. So if we look at a first order reaction like this, which I'll show you on the next slide or two, CH3NC yields CH3CN. As the temperature increases from 190 to 250, the rate constant goes from 2.52 times 10 to the negative fifth per second to 3.16 times 10 to the negative third per second. So it's a big increase there, 2 powers of 10 with just a 60-degree difference. So there's two reasons to explain this, which is why I call it the double whammy effect of temperature on rate of reaction. So the faster the particles are moving, the more collisions we're going to have. So that's number one. Okay? So obviously, faster the particles are moving, the more collisions we're going to have. If I told you in the classroom to stand up and walk around the room blindfolded, you would smash into each other, every now and then. But if I told you to stand up, blindfold yourself, and just book it around the room and go, run around as fast as you can like crazy, you're going to collide way more often, right? So it's the same thing here with an increase in temperature. Second point, number two, the higher the temperature, the more energy the particles have. So when the collisions do happen, a higher percentage of them are going to be more effective, or they're going to be effective. So we have more collisions with more energy. Okay, so it's both things going hand in hand there. If I have you stand up and I blindfold all of you and you walk around the room and you collide, it might hurt a little bit, right? But if I have you stand up and I blindfold all of you and tell you to dead sprint around the room, when you smash into each other, it's going to really hurt, okay? So you're going to collide more often and it's going to hurt a whole lot more. So the general rule of thumb is for every increase of 10 degrees Celsius, the rate of reaction doubles. You don't really need to memorize that, but you do need to know these two explanations here for that double whammy effect of temperature on the rate of a reaction. So let's talk about something called activation energy real quick, since we referenced it earlier in the lesson. Arrhenius, which is the acid-base guy, which we learned about a unit or two ago, he said in order for a collision to be effective, molecules must possess a certain amount of energy, a minimum amount, when they collide to break or form bonds. So the Maxwell-Boltzmann distribution kind of showed us that. In order to form products, bonds must be broken on the reactant side, and particles must have a certain kinetic energy when they collide for an effective collision. So at certain temperatures, only a certain number of molecules have that required energy, or that activation energy, in order to have effective collisions and the reaction to proceed. So that's why the Maxwell-Boltzmann distribution is so important from earlier in the lesson. So we represent activation energy by E sub A. All right. So the activation energy is the amount of energy that needs to be added to get particles up to the necessary amount of energy for effective collisions. So here's our definition of activation energy. It's pretty easy to understand. And again, it's E sub A. So how much activation energy is actually needed for a reaction to occur? It varies from reaction to reaction. I think this is really cool. You may remember or not remember this nitrogen triiodide video I'm going to show you from Chem 1. So sometimes students think the amount of energy needed to activate a reaction, or that activation energy, is a really high amount, or a large amount, and that's not always true. So here's a quick video of nitrogen triiodide, which is Ni3, decomposing into N2 plus I2. And it's not balanced, but we could easily balance that. All right. And if you see the clip, you should recognize this from Chem 1, and I think it's pretty cool reaction to show you. Sometimes activation energy really doesn't need to be all that much.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
Okay, great representation of activation energy here is a guy pushing a boulder up a hill, and he wants to get to the bottom of the hill. So if you have any experience with this, or if you just think about it a little bit, you need to push this boulder to the top of this hill here. And once you do that, the hard work is over. The reaction is just going to go. That boulder is going to fall down to the bottom and go down to level B. So we say from the beginning part of your reaction, so here's point A, up to the peak of your energy curve here. That is your E sub A, or your activation energy. This is given a numerical amount, like quantitative amount. We'll see that on the next slide or two. And then once that occurs, the reaction is basically free to proceed. All right. So a good example of this is water. So we have H2 plus O2, and the hydrogen and oxygen, there's energy stored up in those bonds, right? There's chemical energy stored in those bonds, which we know, and that is some potential energy. So let's say it is X amount right here, where we're starting. what's going to happen is the H2 and O2 are going to combine, and they're going to combine to form something called an intermediate, which we will define later. So you have this really unstable, complex substance here. So we call this our intermediate. This has a very high energy value. Let's say that's Y. All right. That's very unstable, high energy state, so it's not going to want to stay like that. It exists and then goes to something else very quickly. Let's see what happens then. So we saw, again, we were here, our starting point. The H2s and the O2s come together, form an intermediate, and very quickly break apart into H2O. And we end up down here at level Z. All right, so again, X is where we started. Some energy value, some kinetic or potential energy value here. Chemical bonds storing that energy. Intermediate is formed, high energy, unstable state, and then energy is released down to level Z. So this is something called an exothermic reaction, which I know we're familiar with, but we started at level X and we ended at level Z, which is lower. So energy was released in this process. So that tells us that the bonds created here in H2 and O2, or H2O, I should say, the bonds created are very, very strong, and a lot of energy is released when those bonds are formed. Okay, so another example of this is the rearrangement of acetonitrile, which is kind of cool to look at here. We have a CH3, like a methyl group here on the left-hand side, single bonded to an N triple bond carbon. What's going to happen is this N triple bond C is going to rotate, and a certain amount of energy is needed for that to happen. Okay, so the activation energy is going to be required for this to start to rotate. Okay, you see it right here. It becomes perpendicular to that methyl group. And then once that occurs, the rotation is free to happen the rest of the way. And then we could actually create our methyl group bonded to carbon triple bond nitrogen. Okay, you could even see, like, what you have on the right should be more preferred, right? You hardly ever see a lone pair on carbon, right? That's not very common at all. Over here, though, a lone pair on nitrogen is very, very common. So that's definitely going to be the preferred state over here compared to over here. But you still need to have some energy put in to get this bond here to break and for you to have that rotation of that nitrogen-carbon triple bond. So let's look at this graphically, same reaction. So we're going to end things for today. Here's our here's our initial substance over here. Methyl group and triple bond carbon. They're a lone pair on it. Okay, let's say that has 50 kilojoules of energy stored up in those chemical bonds. So the potential energy of that substance is 50 kilojoules. That's the chemical energy it possesses. The question here is asking you, is this an endo or exothermic reaction? So we're starting at 50 kilojoules. We have to put some energy in to get up here. Okay, so here's our activated complex, which we had on the previous slide, or transition state. Okay, that's what this is right here. So I mean, you're not going to see a nitrogen-carbon triple bonded substance perpendicular to a methyl group. Like, that's definitely not going to happen. But that is the transition state here. It's a very short process. Like, it doesn't last very long. All right, and then once that occurs, the rest of this rotation is free to happen, and we eventually end up at our product, which is the methyl group bonded to the carbon triple bond N. Okay, so this is definitely going to be an exothermic reaction because we started at 50 kilojoules, we went up to 85, that's that high energy state of our transition state here, and then we fell down to 35, which is where we are here. Okay, we had a net loss. We lost 15 kilojoules. All right, so this is definitely an exothermic reaction that's occurring here. Okay, some other questions I can ask you here. What is the activation energy? So if you have a curve like this, the activation energy is E sub A. It's right here. It's from where you start up to the top here, just the top of that hill. So it looks like that is 35 kilojoules. A couple other questions I could ask you. What's your delta E? That's your overall energy change. Already defined that. That is negative 15 kilojoules. Okay. I can ask you what the energy is of your product, and that is going to be 35. Just reading the graph is very easy. Energy of your reactant is 50. kilojoules. The energy of your transition state is 85. Okay. It's really about it. I could ask you a couple more questions, though, about the reverse reaction as well. And that's what I'm going to have here on this slide. So it says, what's the change in energy for the reverse reaction? If I want to go back, starting here, reverse reaction is just going this way, obviously. Okay? So the reverse reaction, see it says exothermic in the forward direction? So in the reverse direction, I'm starting at, what was this? This was 35. I'm starting at 35 kilojoules. I'm ending at 50 for the reverse reaction. So there's a net input, okay, input of 15 kilojoules. So the reverse reaction, change in energy, plus 15 kilojoules. Another question says, what's the activation energy for the reverse reaction? It's a good question. The activation energy, and ignore what you see on the screen here because this is for the forward reaction. Let's get rid of that so we're not confused. The reverse reaction, we're starting here and ending here. Not ending, but we have to get to here. Look at that energy difference. Okay, so activation energy is from where you start to that peak, right? So it looks like we have, this was 85, right? So we started at 35 and went up to 85. So that EA is 50 kilojoules for the reverse reaction. Okay, so reverse reaction endothermic, overall energy change is plus 15, and it is an activation energy, though, of 50 kilojoules compared to the 15 that we had, or I'm sorry, the 35 that we had on the forward reaction, for the forward reaction. I think that's about it, guys. So make sure you label the activated complex here. I'm looking at the note sheet in front of me. There's something to label there. And then you should have gone through, you can always rewind and watch again if you need to, but you should have labeled these different components here that we talked about for the forward and reverse reaction. You're going to see those again in the future. All right, guys, I think that takes care of it. That's collision theory. If you have any questions, let me know. See ya.